kernels are classified into monolithic kernel and microkernels. In monolithic kernel architecture, all kernel services run in a kernel space. Whatever the kernel space we have provided to run any of the services, everything will be running on the same kernel space. Here, all kernel modules run within the same memory space under a single kernel thread. Okay, what all the modules are there, what all the tasks are there, everything will be running in the same memory space in a single kernel thread. The tight internal integration of kernel modules in monolithic kernel architecture allows the effective utilization of the low level features of the underlying system. Okay, what all the low level features are there, everything can be used within this architecture, monolithic architecture, because every part means all the modules will be running in the same module of the kernel. For that reason, you will be using all the low level features also to run your all services and modules of kernel. Okay, the major drawback of monolithic kernel is that any error or failure in any one of the kernel module leads to the crashing of the entire kernel application, because each and every modules are running in the same memory space. If any hanging or if any error occurs, it may end whole kernel space only, it may crash whole entire kernel space. Okay, Unix, Solaris, MS-DOS kernels are examples of monolithic kernel. All those things are examples for the monolithic kernel. In monolithic kernel, the architecture representation of the monolithic kernel is given in the figure, that is applications, and you will be having monolithic kernel with all the operating system services running in the kernel space only. As I told you, what all the modules are there, what all the tasks are there, what all the applications which has to be run, or what all the services we have to run in the kernel, everything will be running in the same kernel space. That's why it is called as a monolithic kernel. Okay, it will be interacted with the external application. Next we have microkernel. The microkernel design incorporates only the essential set of operating system services into the kernel. See, whenever you are seeing related to microkernel, always it will incorporate the essential sets of operating system services. What all the main essential sets, what are the basic needs of your main kernel application, that will be incorporated in the kernel. The rest of the operating system services are implemented in programs known as servers, which run in user space. Whatever the other parts are there, implementation, other operating system services are there, they will be implemented in servers and it will be running in the user space. It won't be running in the kernel space. Okay, this provides a highly modular design and OS neural abstract to the kernel, and they provides the highly modular design. Means whatever the design we are providing, means you will be having the some parts in the server part, some parts in the kernel part, you have to interconnect with them. That's why OS neural abstract will be designed for this type of microkernel. Memory management, process management, timer system and interrupt handlers are the essential services which forms the part of the microkernel. Mean within the microkernel you will be having memory management, process management, timer system and interrupt handler. All these things are essential parts or essential services which will be run inside your microkernel. Okay, and MASH, QNX and Minix 3 kernels are the examples of microkernels. You can see here the block diagram or representation of your microkernel architecture is shown here. One is, main thing is microkernel is essential service like memory management, process management and timer management will be running inside the microkernel, and the remaining services are kernel services running in the user space. Remaining any other services are there that can be run in the user space, and applications should be interacting with the user space also, your kernel space also, because your functions and services are divided into two parts. one will be running in the kernel space, another parts will be running in the this thing user space. That's why application should interact with both your user space and also microkernel space. Okay, and in microkernel based design approach offers the following benefits. One is robustness, configurability. If I am going with robustness, if a problem is encountered in any of the services which runs in the server application, the same can be recognized and restarted without the need of restarting the entire operating system. See, if any problem occurs in the application or service which is running inside the user space or server space, if any problem occurs or if any error occurs, no need, it won't crash the whole operating system. You can simply stop that application and you can restart that application only without restarting overall entire operating system. Okay, thus this approach is highly useful for the system, for systems which demands high availability. This approach is highly useful for the system always, and it demands for the high availability. Since the services which run as a server are running on a different memory space, the changes of uh, corruption of kernel service are ideally zero, as the servers will be running the different running in the different memory space. The changes of corruption of kernel services are ideally zero, because all the services which are not in high level of priority will be running in the server or user space. There, if any problem occurs, it won't be affecting our kernel services. That's why kernel service corruption of the kernel services will be ideally zero. Configurability is any service which run as server application can be changed without the need to restart the whole system. If any problem occurs, as I told you, in the server or in the user space, whatever the applications we are running, if any problem occurs, without change, without restarting the whole system, we can change in the server only, and this makes the system configurable dynamically configurable, because in the server what all the changes we want to do, we can do it, no need to restart the whole system only. That's why dynamically in between, if you want to do the changes, you can do it. Next, we have types of operating systems. In this, depending on the type of kernel and kernel services, purpose and type of computing systems, where the operating system is deployed, and the responsiveness to applications, operating systems are classified into different types. One is general purpose operating system, real time operating system, that is GPOS and RTOS. In the general purpose operating system, the operating system which are deployed in general computing systems are referred as a general purpose operating system. The kernel of such a general purpose operating system is more generalized, and it contains all kinds of services required for executing the generic applications. What all the generic applications are there, all those things you can execute in this kind of operating systems. It is general for any type of application. If you want to run any calculator, you can install the application, you can run it. If you want to run the Word document, you can install it. If you want to run the control operations, you can install the control operations and you can run it. That is a general purpose operating system. Generally, you can run anything in these devices. For example, you can take it as your laptop, desktops, your mobile, all those things are general purpose operating systems. You can run as what all type of applications you can do it. Okay, general purpose operating systems are often quite non-deterministic in behavior. Their services can inject random delays into application software and may cause slow responsiveness of the application at unexpected times. It is non-deterministic. If I am running one application, in between randomly you can inject any other application software, it can delay the main program execution. That may be unexpected with respect to your applications running in the general purpose operating system. GPOS are usually deployed in computing systems where deterministic behavior is not an important certain criteria. Here behaviorally it won't be checking anything related to your general purpose operating system, related to what all the functions we are going to run in your general purpose operating system. That is the main criteria here. Behaviorally how it is working with respect to the what type of function it is doing, no, it is not an important criteria related to general purpose operating system. Personal computer desktop system is a typical example for the system where GPOSs are deployed. Windows XP, MS-DOS, etc. are example for general purpose operating systems. Next we have real-time operating system, RTOS. Real-time implies deterministic timing behavior. Deterministic timing behavior in RTOS context means that operating system services consumes only known and unexpected amount of time regardless the number of services. Regardless of the number of services, the deterministic timing behavior of the in RTOS context means the operating system services consumes only known and expected amount of time regardless of the number of services. Here if you have hundreds of tasks, hundreds of services, it won't check for the number of services, but whatever the function or whatever the operation we have given or whatever the services we have given, if it is provided related to the time, one service is there, service or one whatever the service we have related to that, how much amount of time we have given as a delay or given as a execution time. One program is there, that program has to be executed within 1 millisecond or 1 microsecond, then within that much amount of time only it should execute and give the result. Okay, that is a real time operating system. If you have hundreds of programs, but whatever the program is there, each and every program has to execute in its own time, given real time. Okay, and if you have any interrupts in between the main program, if you have any interrupts in the real time operating programs, then also it should have a whatever the amount of time we have provided for that real time program, it should execute within that much amount of time only, with or without the interrupts also. A real-time operating system or RTOS implies policies and rules concerning time-critical allocation of the system resources. The RTOS decide which application should run in which order and how much time needs to be allocated for each application. That is called as, you can call it as an scheduling or interrupt priority level of scheduling. Means whenever we are operating related to real-time operating systems, which implies the policies and rules, always you have to follow the rules and policies related to concerning to uh, time critical allocation, which is having the high level of priority and also which needs to be executed within the less amount of time or within microseconds or nanoseconds, then that should be allotted as a highest priority program or highest priority task. Okay, that's why the RTOS only will decide the which application has to run in which order. Okay, how much time needs to be allocated for each application, that also will be provided for towards the application by real-time operating system. And predictable performance is the hallmark for of a well-designed RTOS. Whatever the predictable performance is there, which is the hallmark for a well-designed RTOS. This is best achieved by consistent application of policies and rules. Policies guide the design of the RTOS. Rules implement these policies and resolve policy conflicts. That is, policies will guide how to design your RTOS, real-time operating system, and how to align each and every uh, part of your RTOS. All those things we can see. Yeah. What all the policies we have, which will guide us to generate the real-time operating system. Rules implements these policies and resolve the policy conflicts. If any conflicts are there, that can be solved by using the rules. Next is Windows CE, QNX, VxWorks, and Micro C or OS2, OS2, etc. are the example of real-time operating systems. The real-time kernel. The kernel of the real-time operating system is referred as real-time kernel, and the real-time kernel is highly specialized and it contains only the minimal set of services required for running the user applications or tasks. The basic functions of real-time kernel are task or process management, or task or process scheduling, task or process synchronization, error or exception handling, memory management, interrupt handling, and time management. All these things are the basic function of real-time kernel, because whenever we are considering or talking about any real-time operating system or real-time operations, then always the main thing is task or process management, how we are managing to execute the highest priority programs or tasks, or and task or process scheduling, how we are scheduling it, which is having the highest priority, which has to be executed after that execution, after the execution of the second program, which has to be executed, that is scheduling. Next is task or process synchronization, how it has to be synchronized with the other programs or data, which data has to be included for the execution, or which data has to be accessed for the execution of your program, that is related to synchronization. Error or exception handling, if any error occurs in between the execution of real-time operating system, it should not wait for the verification of that error, or it should not for the wait for to resolve that error. Always you have to come out of that error and once again go back and once again execute it. That is error and exceptional handling, how we can handle the error and exceptions. And memory management. Memory management, whenever we are seeing related to process and task and all, the data requirement related to the highest priority process or task should be given first, and then you can go for the least priority manage task or process. That's why memory management will also come into place in real time kernel. Next we have interrupt handling, how we can handle the interrupts. Means if the main program has to be executed within the 10 microseconds, within that much amount of time only it should execute. If you are getting any interrupts, then how much amount of time we can provide for the completion of that interrupt, that everything we can see in the interrupt handling. Time management, as I told you, real time always dependent on the time. If it has to be executed within 10 microseconds, then always it should execute within the 10 microseconds only. If or else less than 10 microseconds, more than that it should not go. It may lead to the disastrous destructions, or it may lead to the loss of the human, or loss of the equipment, or loss of the whole industrial environment only. For that reason, always time management is also critical thing in real-time operating systems. Next is the real-time kernel. In that, task or process management, one by one we will see how we can manage the task or process everything. That is, task or process management deals with setting up the memory space for the tasks. What all the memory space are there, that will be set up for tasks, and loading the task code into the memory space. You have to load that tasks or process into the memory space. Allocating the system resources, what all the resources we need to execute, our resources are needed to execute the task, that also has to be allocated. And setting up the task control block for the task control block will be generated, and in that you will be having which task has to be executed, how much time it has to take to execute that one, what all the resources are needed, is it available or not, all those things we can see in the task control block. Task process termination and deletion, that part. And a task control block is used for holding the information corresponding to the task. Task control block is always is used for holding the information, whatever the information is there, that can be hold. And you can see here what all the information will be present in your task control block. Usually contains the following set of information. First is task ID, task identification number. Normally I can take it as 10 tasks are there. I am representing each and every task with the task identification number 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. In that way, if I am taking the task for 1, then task identification number will be 1. Task state, the current state of the task. Example, state is ready for the task which is ready to execute. If it state of the task is ready state, then task is ready for the execution. Task type, and that indicates what is the type of the task. The task can be hard real time or soft real time or background task. Three type of task will be there, that is with related to real time operating system. One is hard real time, soft real time, and background task. Hard real time if is a real time task where the execution of the program should be very critical. Means if I have if hard real time is there, means if the task has to be executed within 5 microseconds, the execution should be completed with before that 5 microseconds only. Soft real time is if any if I am taking the time slot of 10 microseconds, if the task execution is taking more than 10 microseconds also, which won't affect the system or which won't affect the overall industrial environment, then it will come under soft real time. Background task is how much hour of time you want to take for the execution of that task. You can take it, it won't affect any other thing of your overall system, that you can take it as background task. I will give it an example, that is your clock inside your system or clock inside your mobile, anything that will be running in background only, because it won't affect your overall systems. Simply to see or watch the dates and times, we are using that background task. Okay, then task priority. Priority is equal to 1 for the task with the priority 1. Remaining tasks will be having the remaining numbers related to their priority. And task context pointer, pointer for the context saving, and context memory pointers to the code memory, data memory, and stack memory of the task. It will provide the pointers, means you will be having the address of that context, address of the memory, address of the data memory, address of stack memory, all those things will be there. And task system resource pointers to system resources, that is semaphore, mutex, etc., used by the task. Next is task pointer to both TCVs for preceding, next, and waiting task. That is task pointers uh, related to next task control block. See, task pointer, first you will be executing using this main task control block. Next, whatever the task you want to execute, that will be pointing towards the next task control block. Other parameters are other relevant task parameters will be considered here. Then the parameters and the implementation of task control block is kernel dependent. Whatever the parameters are there in the task control block, all these things are dependent on the kernel. Okay, and the TCB parameters vary across different kernels based on the task management implementation. Uh, Related to what all the type of task management we are using, related to that the parameters which are present in your time task control block will also change. And task management services utilizes the TCB of the task in the following way. One is creates a TCB for a task or creating a task. Okay, and delete or remove the task control block of the task when the task is terminated or deleted. Whenever it is terminated, you can delete it. And read the task management service utilizes the task control block of the task in the following ways. One is it creates the TCB whenever the task is creating on creation of the task. Next, deletion on or removal of TCB of the task when the task is terminated or deleted. Whenever it is getting end or whenever you are deleting the task, that TCB also should be deleted. Reads the TCB to get the state of the task. Whenever we want to see in what state the task control block is, then you have to read that task control block. Update the TCB with the updated parameters on the need basis. For example, on the context of switch. Context is if I am switching from one task to another task, then you have to update that in what state the task is, and also what is the resource address. All those things will change whenever you are shifting you are doing the context switch. And modify the TCB to change the priority of the task dynamically. Dynamically you can modify the TCB to change the priority of the task. And task or process scheduling, where deals with the sharing the CPU among various tasks or processes. A kernel application called scheduler handles the task scheduling. As I told you, task or process scheduling, you will be arranging them. One task is executing means its priority should be verified, and what amount of time it has to be executed, that also should be verified, and then it will be scheduled in the top priority. After that next one, after that next one. In that way you will be arranging one task by another task by taking the considerations of its priority, considerations of its resources allocation, consideration of its execution time, consideration of is it a hard real time or soft real time or it is a background program. All those things you have to consider while doing the scheduling function. Scheduler is nothing but an algorithm implementation which performs the efficient and optimum scheduling of tasks to provide a deterministic behavior. To provide that deterministic behavior related to the program or task, you will be you will be going through this task or process scheduling. Okay. Task or process synchronization deals with the synchronizing the concurrent access of the resources, and which is shared across multiple tasks, and the communication between the various tasks. Task or process resynchronization, whenever we are going related to synchronizing the concurrent access of the resources. Parallelly you are accessing the see 2 to 3 tasks are there. All the 3 tasks want one same data or same resource information. Then you will be concurrently connected with that resources, and you will be accessing those resources from same memory area, that is which is shared across multiple tasks, and the communication between the various tasks. Communication also should be done between the various tasks. See, one task is using the same resource, like if I am telling you an example, A. if I am taking a data from the memory address, that is A, I am taking for task 1, but task 2 is also waiting for the same resource, then it will be communicating with the previous task. That then if after the completion of that task, you can take that data A from the resource or A from that previous task. Okay, that's why communication and synchronization has to be done between the task or processes. Next we have error deals with registering and handling the error or occurred exceptions raised during the exception of task, and insufficient memory, timeouts, deadlocks, deadline missing, bus error, divide by zero, unknown instruction execution, etc. are the example of error or exception. If any unwanted thing happened, or if what all the memory we have used for the code, if it is insufficient, for data if it is insufficient, timeout, as it is real-time kernel, always you should be constraining related to time, deadlocks and deadline missing. Deadlock means both the programs are running and both the programs are waiting for the same resource, then it will be a deadlock form. And deadline missing, bus errors, divide by zero is infinity. If I am getting into that infinite loop, then you can't come out of that, that is also error. Unknown instruction execution and etc. All these things are error and exceptions. Error or exceptions can happen at kernel level services or the task levels. Deadlock is an example of kernel level exception, whereas timeout is an example of the task level exception. Example of kernel level execution, whereas timeout is an task level exception, that you can see. And operating system kernel gives the information about the error in the form of system call. And watchdog timer is a mechanism for handling the timeouts for task. If any timeouts occurs related to task, then watchdog timer will